We covered the conics in a previous video, but you can't eat the cone unless it's an ice cream cone, but I'm going off on a tangent. The torus, however, is rather delicious, and they don't start selling donuts from until you get to December. Well, that used to be the case, but these days December starts in mid-October, something like that. But, keeping up with traditions, I bought a box of donuts! It's not the glazed kind my American viewers might be accustomed to. I didn't have one of those until I was 7 and a franchise clan opened a restaurant in my neighbouring town, and thus they have no nostalgic value to me. However, they're also too sticky for studying the not so popular custom of the conic section, namely toric sections! Just as with the conics, we get our curves from the planar cross section of the torus, but unlike the conics that can all be summarized by a quadratic equation, the torus needs a quadratic equation to be fully described. To bring this point home, we will start off with a general equation for a conic section, namely now, as we can see, every conic from the previous video can be described by substituting in for A, B, C, D, E, F, as long as A, B and C are not all 0. As an example, if we have A is equal to 1 over B squared and C is 1 over A squared, and we have that B and D and E are all 0, and we let F equal to -1, then we have an equation for an ellipse. You can do the same for all the other conics, just substitute in and you will get whatever conic you would like. In just the same way, every toric section can be described by this quadratic equation. Various toric sections can then be classified by the angle to the axis of rotation and by the distance from the plane of intersection to the origin. Now, if we have donut, where the axes are x, y and z, if we were to name the distance from the origin to the center of the circle of revolution, big R, and we name this distance small r, then we can write and we will now use this equation to derive the equation for the first class of toric sections we will investigate, namely the spiric sections, where you can see that the plane of intersection is parallel to the axis of rotation. So I'll swap around the board and we will start off with the equation for a toric. Now we will interchange the y and z component. And next we will replace the c with the component d, where d is the distance from the origin. And then we expand both sides. And all of this is equal to Take note that we have big R squared, x squared. If we subtract this from both sides, well then this one becomes negative. Same thing to this one. And now we'll collect some terms. So we have the x and the y to the fourth, and we have this xy term. So we can collect them as so we have that all of this is equal to this thing, which is equal to 0. And to bring home the comparison between this expression and our general toric, we have that It must, however, be noted that the equation for spirates this expression does contain curves that are not part of the cross-section of a torus, unless you let the plane of cross-section be imaginary. But that's sort of out of the scope for this video, so we will keep this equation as is. Now that we have the equation for a spirac section, we will investigate two special classes of the spirac sections. First off, we have the hippopede. I said hippopede, but there is a relevance. Under the toric definition of a hippopede, we have the plane that intersects parallel to the axis of rotation and tangent to the inner circle. We are allowed to change the radius of the circle and the radius of revolution. We are even allowed to let the torus intersect itself, but I prefer my donuts with a hole. That's why I eat them like this. Hashtag control topology. Typical equation for a hippopede. We let this gamma be 0, and we would let some further classifications can now be made. In the case that beta is greater than 0, we have the oval of Booth of the Irish mathematician James Booth. Should beta be less than 0, well then we have the lemniscate of Booth. In the case that alpha and beta are both equal, we get the lemniscate of Bernoulli, which is also a special case of the next class of conic sections we will cover, namely Cassini ovals, named after famous mathematician and astronomer Giovanni Cassini, who studied them as an alternative to Kepler's elliptical orbits for planetary motion, I believe he held even off Newton's Principia, based around an erroneous assumption that the Earth is elongated at the poles. And today that may seem a bit unreasonable, but at the time the debate was not really settled, and it wasn't until the French geodesic mission in 1736 that the matter was truly resolved. I've put the link in the video description to an article that compares Cassini and Kepler's orbits to show that it wasn't all that unjustified. Now, for the formal definition of a Cassini oval, we have the locus of all points where the product of this distance and this distance is a constant. We can write this out as when expanding this thing, we get that x squared plus y squared is equal to 2c squared times x squared minus y squared plus a to the fourth minus c to the fourth. Now we have the equation for Cassini oval, but in our toric parameters we need to note that we only have a Cassini oval when the distance to the plane of intersection is equal to the radius of a generating circle, or small r in our case. Let's just start with the equation for a torus. And now we're going to do, so we're going to do the same, we're going to interchange c and y. And the new c component is going to be the distance, as said, that we only have a Cassini oval when this thing is equal to r. So we're going to place in a small r and a small r as well. Oh, we almost forgot this whole thing is squared. And then we expand. Now, let's not expand immediately. R squared minus r squared. So we're going to make things a bit easier on ourselves. Now, just as before, we have some similar terms. So we have this r squared term, r squared, x squared term, but we don't have the y, so we can just subtract this one, and this leaves us with and as we see, this is clearly a Cassini oval when we let C equal R and we let A be equal to R, big R, small r. Now, in order to collect our results, we have that for the Cassini oval. So I add this thing to the bottom, This epsilon characterizes the shape of a Cassini oval in sort of the same way as an eccentricity would characterize an ellipse or hyperbole. But it's defined as the square root of 2 big R times small r all over big R. And when this epsilon is less than 1, we have 2 separate loops, and as epsilon increases, it becomes more and more egg-centric, because it's the shape of an egg. When it becomes 1, we once more have the lemniscate of Bernoulli. When it's greater than 1 but less than the square root of 2, we get this peanut shape. And when it's greater than the square root of 2, it becomes convex. Next up, we have the toric sections, where the plane of intersection is perpendicular to the axis of rotation. And these are not that spectacular, as they mostly form the boundary of an annulus, except for the situation where the distance to the origin is plus or minus small r. For completeness, I derived the equation by substituting d for c in the equation for torus, yielding and that's pretty much it for the annular sections. Finally, we have the toric sections, where the plane of intersection is oblique to the axis of rotation. There are quite a bit of cases that we could consider, but we're only going to look at one of particular interest, which is the Virasor circles. And just as the plane of intersection comes down and becomes tangent to the torus at 2 points, we get 2 perfect circles. To show that this is the case, I constructed my own argument based on Anton Hirsch's treatment, the link in the description. So, if we now have these two are the circular cross section of a torus, then the inner tangent, just going to eyeball it down through the x-axis. If we name this theta, this angle right here, so you could sort of imagine, okay, so this is the right angle triangle, then you could say that, okay, so you know that this distance, that will be the hypotenuse of this right angle triangle. We know that this distance is r, and we know that this distance is small r. So we know that theta is the inverse sine of r over big R. If we now were to construct, let's do this in blue. If we now were to construct a new triangle, we have that this distance is x and this distance is y, or is set in this case, since, so we have, let's say that this is the x-axis, the y-axis come out, the z-axis goes straight up. So this distance is x. Then we have that so this thing will just become the hypotenuse of this blue triangle. and we have to multiply by cosine of theta in order to get the component along the x-axis. Similarly, we can now make an expression for the slope as another way to write the tangent, in this case, and we would just like to have the c term by itself, and we also would like it square, so we're going to multiply it out in x, and we're going to square both sides, so we get another way we could write this bottom expression would be it's not all that important right now, but we will use it later on. And now, if we recall the equation for a torus, we've been here before. We will substitute c squared for this thing, so we get notice that we have an x squared and an x squared over here, so we're going to rewrite this as and now I'm going to get a bit cheeky. So we have this arm, and if you can agree with me that a torus is still a torus, even though we've shrunk down small r to nothing, i.e. we're letting small r become 0, then we are left with the equation so if we now I've forgotten, so we still have this thing going on. If we expand this one, we have so now we have this thing, we're going to just combine stuff. So we have and now when we have this expression, so take note that we have a minus 2 r squared something. Here we have an r to the 4th, and here we have an x squared plus y squared, and we have an x squared y squared squared. So you could sort of do a substitution. Let's call this u and this thing u, and then we see that we have a quadratic equation, and so we could rewrite all of this as, and this sort of concludes the argument. If you are able to recognize that x squared plus y squared minus r squared, well, this is just a circle equation, and well, at least in order for this to become 0, but take note that we have this whole thing squared, and that sort of entails that we have two circles, because we must have two solutions for this thing. And so we know that we have two circles, both with the radius big R, in order for this to become 0. Another thing to note, because of this expression underneath, so if we were to allow R to be non-zero, we can sort of see that we get a symmetric relationship, so we get two circles that are symmetric about the x-axis. This more or less concludes our investigation into toric sections. There are some interesting relationships between toric sections and conic sections that I would have liked to cover, and also between Hoof vibrations and their source circles, but that has to be for another video. Anywho, next time you're cutting a bagel or have a donut, you have the mathematical tools to help you out, and I guess all that's left to say is thanks for watching and keep it interesting.